Today we'll continue our look at logic operations by looking at shifting instructions. And to start with, let's look at shifting left. Now, the shift left instruction is quite straightforward. It takes a register to store the value, a register where the value is, and a value to shift by. So if we give it 1, we shift the number to the left by 1 position. 3, we shift by 3 positions, and 2, we shift by 2 positions. And you can see this down here with the binary representation. These grey zeros are the values that the assembler inserts to shift to the left. So you have to put something in, and you put 0 in that case. Now, why do we care about shifting left? Well, we care because it's equivalent of multiplication. If we shift left by 1 position, that's the same as multiplying by 2. If we shift left by 3 positions, that's the same as multiplying by 8. And if we shift left by 2 positions, that's the same as multiplying by 4. So this is a handy way to emulate multiplication via even numbers. Now, the reason this is good is because it's faster than using the mul instruction. So it used to be much faster. Now it's about 3 times faster roughly, but we don't really need to worry about the details of that. An important thing is that a good compiler will automatically optimize the multiplication to take advantage of the shifting left rather than multiplying directly. So for example, if we have that b is going to be equal to a times 640, it might be compiled as if it were a shifted left by 9 positions plus a shifted left by 7 positions. Why we would do this is because this is equivalent to a times 512 plus a times 128, which of course will be equal to a times 640. So this is going to be quite important for us. We'll have to do this by hand, but it's an important thing to remember. Another use for shifting left is array access. So if we assume that A0 contains the address, so it's a pointer of an array of words, and A1 contains the index, you can think of that as what we usually call I in a Java loop of the array. Here's the standard way of extracting A0 at position A1 into a register V0. Well, we take the index and we shift that left by 2, and that's the equivalent of multiplying it by 4. So we know that a word is of size 4, so every time we look to the next word we need to increment by 4. If our index is being updated, for example in a loop, then every time we could just multiply the index by 4 to get the actual correct offset. Then what we would do is we would add to the address of the array the new correct offset, and that would get us the correct memory address, and we could then load from that position into V0. We can also shift left by a variable amount, and this is quite handy. So if you were thinking of setting up a loop, it might be handy to have a value stored at a register that you just want to manipulate every time you go around it. So here we've loaded in a hard-coded value of 03E9, and we're loading in 6. And you can see there that we can shift left by variable amount. That's shift SLLV is by the variable amount. And then we just shift the value in T0 by the value of T1. In this case, we'd shift 03E9 by 6 to get us FA40. So let's think about how we might use this. If we wanted to write code to place 2 to the power n in register V0, if the value n is stored in A0, how might we do this? If you want to do this yourself, I'd recommend pausing it now before I dive into the answer. Okay, so what we'd do is we'd load an immediate value of 1 into V0, and this represents 2 to the power 0. So if there is a value of 0 in A0, that's the correct value to have there stored by default. It's kind of our base case. And then we just shift left by a variable amount, applying it to V0 using A0. And that's all there is to it, because shifting left in binary is equivalent of 2 to the power of however many places you shift, or multiplying by that. So, for example, if A0 contained 1, we would shift the value of 1 to the left. That would get us a value of 2, which is equal to 2 to the power 1. Now, of course, this is true for any value of n, but that's just a simple example of how you might want to use shift left. Now, similarly, we have shifting to the right by an amount specified. This is extremely similar to shifting left, but we do it to the right. The syntax is much the same, it's just the meaning that's different. So you can see here we're inserting these grey values of 0 in order to shift the value down to the right. Now you might also think that we're losing information here, and we kind of are. We're losing a little bit, and that's because we're not taking account of decimals at the moment. We're just rounding down when we do the shifting. So why do we care about shifting to the right? Well, that's because this is equivalent to division by powers of 2. So similar to the shifting left examples, here you can see that shifting left by 1, 3 and 2 are equivalent to dividing by 2, 4 and 2, 8 and 4 respectively. So we can also do this with a variable amount. Again, this is very similar to shifting left. The syntax is the same as you can see here, it's just that you shift right by SRLV, that's the variable amount instruction, and it does the same thing. So we would care about this because this is the same as division, as I said earlier, but even now this is still much faster than using the div instruction. Again, a good compiler will automatically optimize, and that's something we'll have to do by hand ourselves. But there are, it's worth noting, arithmetic right shift instructions, SRA and SRAV. These attempt to do this in a, in quotes, arithmetic way by representing negative integers, and the way it does that is by extending the sign bit. So if the leftmost bit is 1, it will keep that in to make sure that the negative is kept in place. But we don't really need to worry about that too much now. So at the end of this week, these are all the instructions we should have under our belt. So we've added all of these logic instructions as well as the shifting instructions. The ones above should be familiar to you after the first week or second week as well. But that's everything for today. I hope you found this useful. If you have any questions about anything I've covered in this video, please do get in touch. Thanks.